know that as we grow, the hurdles will be more. Each time we are washed away, we bounce back to the shore. We know we lead the way, keeping on top day. To see the sunrise tomorrow, inspire the world to follow.
Okay, so in the curriculum of electrical machine 1, that is ES3MC1, today our topic is DC generator. We'll cover this module. Okay, and in this lecture we are going to cover the construction, EMF equation, and if time permits, then the types of DC machines. Okay, so let's start module number 2 on DC machine, and this is the objective and outcome of our today's lecture, to become familiar with the construction of DC generator. So let's start lecture number 1, constructional features of DC machine. Okay, so the construction of any machine should be made in accordance with its basic principle operation. So according to the basic principle operation, construction should be done. Now, from our basic knowledge, we know that DC machine can be operated as generator or it can be operated as motor. Okay. Now in generator, mechanical energy is converted into electrical energy. In motor, electrical energy is converted into mechanical energy. So constructional requirement can be obtained either following the generator action or motor action. Okay, now whether it is a DC generator or it is a DC motor, the operation of this is the prime criteria to develop the DC machine. Now we know DC generator is basically works on Faraday's laws of electromagnetic induction. So on this principle, DC generator works. And what is Faraday's laws of electromagnetic induction? When there is a change of flux, there is a production of induced EMF. Or we can say whenever flux linking a coil changes, an EMF induced. Whenever flux linking in a coil changes, an EMF induced. Okay, so this is the Faraday's laws of electromagnetic induction. Now, what are the basic requirements that has to be fulfilled to satisfy this Faraday's laws? The first one is field system. Second, system of conductors or coils. And third, relative motion between the above two systems. So this is my requirement that has to be satisfied to fulfill the Faraday's laws of electromagnetic induction. I need a field system, I need a system of conductor or coils, and I require the relative motion between these two, that is the field system, and between field system and conductors or coil. Then there is a cutting of flux and there is a production of induced EMF. Now this third requirement, that is the relative motion between the above system, it can be satisfied basically in two ways. What is that? First, I can keep this field system stationary and allow the system of conductors to rotate, these to rotate, or we can keep this system of conductor stationary and field system to be rotate. Okay, now this is the things when I am going to construct a DC machine, I should keep all this principle into our mind. Now, apart from getting the EMF induced, what else a DC generator require? That this induced EMF, which is basically a AC EMF. This is basically a alternating in nature, and this is a DC machine. So what is my next motto? That this AC EMF induced in the conductor should be converted into DC EMF. This should be converted into DC EMF. And this conversion from AC to DC is achieved by some mechanical rectifier, by some mechanical rectifier, which is known as commutator. Okay, and the brass. Now this brasses basically acts as the connecting leads between the moving number of the machine and the external stationary circuit. So the electrical connection between these two systems, field system and system of conductor, that is the stationary system and rotating system, the connection is basically electrical connection basically fulfilled by this brass. Okay, and where to place this brass? We can place in rotating system or we can place it stationary system, but it is not possible to place in the rotating system. So for ease of operation, it is placed in the stationary part of the machine. Okay, but the commutator part, rather we can say that commutator assembly, however, is placed in the rotating member of the machine along with the system of conductor of coils in which AC EMF induced. But this commutator assembly is placed in the rotating part of the machine along with this system of conductor or coils where that Faraday's laws of electromagnetic induction occurs. Okay, so the above requirement therefore restrict the use of the only option available to. So if I have to satisfy all these, so the conclusion is that there should be a construction part, there should be a field system which is stationary one. So keep that in mind. In DC machine, field system is stationary. Field system, which is the stationary part. Okay, so this is called the stator of the machine, which doesn't move, and normally in the outer frame of the machine. Okay, and there is a rotating part which contains this system of conductor and coils, that is called the rotor. Okay, and both this stator as well as this rotor are made of ferromagnetic material. Made of ferromagnetic material. Okay, so a DC machine has two basic functional components. One is the magnetic circuit, where the magnetic flux is created, moved and confined, and this magnetic circuit comprises poles, armature core, yoke. So this is basically the rotating part, or not rotating part. It's a consist some parts from stator, some parts from rotor. So one is magnetic circuit Another one is the electrical circuit, which contains that armature winding, commutator, brush and pole winding. Okay, and based on these two things, the classification has been done: stator and rotor. The stator is producing the magnetic flux and the rotor is the inner part of the machine. It is also called the armature. So the rotating part is also called armature. So the rotating part is called armature. Okay, so that houses the conductor. So the conductor are placed inside this armature. So this armature is basically houses the conductor for generation of EMF and torque. Okay, and there is a small air gap between this stator and the rotor. Okay, so this is the basic concept. So let me see some pictorial representation of the constructional part of DC machines. So this is a cross-sectional view of inner parts of DC machine. So this is basically inner parts cross-sectional view. So this is basically the cross-sectional view of the inner parts of the DC machines, and these 16 are the members of this DC machine, such as yoke, pole core, pole winding, pole shoe, pole face, armature core, brass, commutator, armature winding, frame. So these are the cross-sectional view of DC machine, and each part has been identified into this cross-sectional view. And this is the different parts which has been shown. Photograph of DC machine stator. So this is basically the DC machine stator. So this is basically DC machine stator, and this is basically showing the rotor. So okay, so the stator is consist of yoke, pole shoe, pole face, pole winding, and this total is called the frame. Okay, and the rotor is consist of like armature slot. So this place are the slot, this place, teeth, windings, commutator, and this is the rotating part of the machine shaft. So these are the rotors. Okay, so stator and rotor. Okay, and this figure is basically shows the brass holder spring and brushes in DC machine. Okay, so let me briefly describe all the parts with their functions. Okay, so let me open the file first. Okay, is the DC generator and motor have same construction? The answer is yes. Both has the same construction. That means it is a reversible design. So same machine can be work as DC generator as well as DC motor. So let me first discuss frame, which consists of yoke. Okay, so if you see the outer part of the DC machine is basically called the frame. The frame of DC machine is the outer cylindrical part. So the frame is outer cylindrical part. The frame is basically outer cylindrical part. Okay, which enclose all the inner parts of the machine. And frame is usually made of cast iron. This is made of cast iron. And what is the function of this frame? The function of this frame is to protect the internal part from outside and hold the static part of the machine. So what is the function of the frame? Protect the internal parts from outside. Protects internal parts and hold the stationary parts. Okay, and what is there inside this frame? That is the part of the stator. Inside the frame are component of field system in DC machines, and this part field system or magnetic system. So frame basically hold that magnetic field system, and which is basically the yoke, pole core, pole shoes, field winding. Okay, so now yoke. So what is the function of yoke? So the yoke main function is to provide a protective covering over the inner sophisticated part of the motor and carries the flux produced by the poles. You should keep that in mind. So yoke basically carries the flux produced by the pole, which is basically a thick cylindrical part of the stator. This is basically a thick cylindrical part. This is basically a thick cylindrical part. This is basically a thick cylindrical part that carries the flux from the pole to pole. So this is the main function, okay, that it provide a low reluctance path for the magnetic flux. So it provide the low reluctance path, which is basically the requirement for any magnetic circuit, to provide the low reluctance path for magnetic flux to complete its path. Okay, so this is the function of the yoke. You should keep that in mind. And the yoke is basically made of good quality iron or steel. So this is made of iron or steel, so that the flux can easily flow through it. This is my main requirement, that it carries the flux. So everything I have to decide keeping that in mind whenever I am designing the yoke. So it is made of iron and steel, so that it can provide a easy flow of flux through it. Okay, so basically cast iron, rolled steel is basically used, and this iron is basically used for small machine, and rolled steel is basically used for larger size of machine. Okay, so this is yoke. And there should be a question for you people regarding this from this yoke part. Okay, that why the yoke is a DC machine is not made of lamination. So why it is not laminated? Why it is not laminated? So you should think why it is not laminated. Okay, now the magnetic field system. Next part is poles, and the poles in DC machines are salient type. It is basically salient or protruding type, because they are project inwards, so it is called salient structure. Okay, and this function of main pole is to create the working magnetic flux. So it creates the magnetic flux, create the working magnetic flux. Okay, it create the working magnetic flux. Okay, for small DC machines permanent magnets may be used. For larger machine electromagnets are used, as permanent magnets are expensive. And the different part of this pole are pole core, pole winding, pole shoe, pole face. So pole core, pole winding, pole shoe, pole face. Okay, So this is basically fitted onto the inner wall of the yoke with screw. You can see the picture. Okay, to see the picture. Let me open the other link. So if you see here, so see, this is the pole and field winding. So this is the basic structure. Okay. So first is field winding. So if you see, this is the figure. Okay. So this is the figure. So this field winding is basically made with copper wire wound over the slot of the pole shoe. So it is wound over the slots of the pole shoe. The field winding is basically from an electromagnet that produces field flux. Okay. So this is made of copper conductor. So if we give a DC supply, this winding require magnetomotive force to create this electromagnetic flux. Okay. Enamel insulated strands of round copper is basically used for small machines to make the pole winding, where for the large machine it is paper insulated rectangular strips of copper conductor. Okay, so basically copper is used. Okay, so this is field winding or magnetizing coil. Okay, so the two part are left. Let me discuss that two part also. So first, three part pole core. So what is pole core? Pole core. So this is the fixed part. This is the fixed part with yoke. So it is the part of the pole which is fixed in the yoke. If you see the diagram, so you see here, so this is the thing. Okay, so this part, this whole part, is which is fixed with this pole is the so this total fixed part is called the core. The total fixed part is called the core. And this pole core is made of low reluctance steel so that it can easily carry the magnetic flux. And the pole cores are not laminated. Okay, you should keep that in mind, it is not laminated. Okay, but in some machine, pole core can be made of stack of laminated sheets of electric steel of around 1 millimeter thickness, which are insulated from each other, okay, by varnish. So this is pole core. Now pole shoe. So this is the pole shoe, is the part of the pole which extend to form end of the pole core. So pole shoe is the extent. So this is my pole core and this is the extensional part. So pole shoe is basically the extension of core towards the air gap. So this is the stationary part, and after that there is a rotating part. So in between there is a air gap is there. And what is the function of this pole shoe? The function of pole shoe is to distribute the flux from pole core to the rotating armature through air gap. So this is the function of pole shoe. It provides the flux from pole core to the armature. So it's basically provides or rather distribute. So distribution of flux from core to armature. Okay. So this is basically done by pole shoe. Okay. The pole core basically has much higher flux density than that permitted at the air gap, and hence the cross-sectional area of pole shoe is greater than the area of pole core. You should keep that in mind. This is the very important point. The area of pole shoe is greater than pole core. The area of pole shoe is greater than pole core. Okay. Why? Because the reason is that the pole core usually has much higher flux density, because the pole core is basically on the winding where the main flux is producing. So here the flux density is higher than that permitted in the air when it is distribution through the air gap. So from which it is getting distributed, the area should be higher, because here the flux density is very high. Flux density is very high. So when it is permitted at the air gap, so the area should be high so that it can fully link up with this armature. Okay. And pole shoe is basically made of laminated sheets of electrical grade steel. Okay. And this is pole face, this part, this extreme part after which there is air gap. This is basically pole face. This is basically the surface of pole shoe that faces the air gap. So pole shoe is basically the surface of pole shoe. So it is given a circular shape to maintain uniform air gap length while the circular armature rotate alongside the pole face. So this is basically give a circular path so that flux distribution should be uniform when the armature is rotating facing this pole surface. The uniformity in the air gap between the pole face and armature surface also ensure that flux line that leaves the pole face perpendicularly also enter the armature at 90-degree angle to the armature conductor which is placed in that armature slots. Okay, so this is all about that magnetic circuit, yoke and the pole. Okay, now armature. This is the rotating part of the DC machines. Okay, and the armature consists of a shaft upon which a laminated cylinder called armature core is mounted. Okay, so and this armature core has grooves or slots of its outer surface. So if you see, this is the armature and these are the slots, grooves. These are the slots or grooves. Okay, so these are the slots or grooves in the outer surface, and the lamination are insulated from each other and tightly clamped together. Okay, in small machine, lamination are keyed directly to the shaft, and in large machine they are mounted on a spider. So the lamination is basically done to reduce the eddy current. So if you see, these are the structure of armature, which is consist of slots to which armature winding are made to several tons of copper wire distributed uniformly over the entire periphery of the core. And these are the air hole for cooling purpose, and this is the keyway or the spider is there, and these are the teeth. These are the teeth. Okay, so let me see if I have a better picture. Okay, so this is the whole rotating part. So these grooves are the slots. Okay, so these grooves are the slots. So these grooves are the slots, and these are the stator teeth, and around this there is armature winding. Okay, this is the commutator where the rectification done, and this is the armature shaft. Okay, so this is the more detailed structure. So this conductor are basically placed in the slots of the armature core, and the conductor are wedged and bands of steel wire are fastened round that core, winded to prevent that flying under the centrifugal force. And this conductor which are suitably connected is from the armature winding, and there are two type of armature winding. One is called lap winding and another one is called wave winding. Okay, now commutator and brass. Okay, so I have shown this is the commutator. This is the cylindrical structure made of copper segment stacked together but insulated from each other. This basically collect the current from armature conductor and convert that alternating current induced in the armature into the DC current. So this is basically acts as a mechanical rectifier. And this is the brass made of carbon and graphite structure. So you should keep that in mind. This is the sliding contact over the rotating commutator. The rotor is armature is rotating, commutator is connected to the rotating structure, and the brass is the sliding part which is collecting the current from the commutator and it is available in the stationary circuit, and that's why sparking occur in this brass segments. Okay, so this is basically the sliding contact over the rotating part. Okay, so this is the main brief idea about that DC machines construction. Okay, DC machine constructional part. Okay, now let me discuss about that EMF equation of DC machine. Let me recapitulate whether I have covered everything or not in the construction. Yes. Bearings. So we later on discuss armature winding in details and the difference between these two types which I have mentioned, lap winding and wave winding. Oh, okay. So EMF equation. Okay. So we have mentioned earlier that as the armature rotates, a voltage is generated in its coil, and in case of generator, the EMF of rotation is called generated EMF. Okay, and is ER equals to ER equals to ER equals to EG, and in case of motor it is denoted by EB, which is known as back EMF or counter EMF. But both for generator and motor, the expression of whether it is EB or EG, it is same. Now let phi is the flux per pole in Weber, P is the number of pole, Z total number of conductor, that is number of slots into number of conductor per slots. So per slots number is multiplied with the number of slots. Okay, N is the armature rotation in revolution per minute, or it can be RPS, revolution per second. You have to keep that in mind whether you are taking RPM or in RPS. Is the EMF induced in any parallel path? Okay, one thing they have not mentioned, let me mention. A is the number of, sorry, here it is mentioned, number of parallel path into which Z number of conductor is divided. Okay, so Z is the total number of conductor and A is the number of parallel path through the armature between brushes of opposite polarity. So Z by A is the number of armature conductor, number of armature conductor in series for each parallel path, for per parallel path. So this is the total number of conductor. So if we divide it by A, we will get the number of armature conductor per parallel path. Okay. So since the flux per pole is phi, okay, so a number of pole is P. Okay. So total flux is my P into phi, that is P phi. So this is the flux conductor cuts in one revolution. Okay. Now generated voltage per conductor. So it is, we know from Faraday's law, d phi by dt, which is average EMF generated per conductor. Okay. Now we have already made P phi is in one revolution in RPM, so n by 60. Okay. So time for one number of revolution per second is n by revolution is take 60 by n. It is very clear. So 1 second, in 1 second the number of revolution is n by 60. Okay. Or rather, if we take it in RPS, so that means n revolution made in 1 second, or we can say 1 second n minus 1 revolution. So n by 60 revolution in 1 second. So 1 revolution in 60 by n second. So that is what I have mentioned. That is my dt. So what is my d phi by dt? So my d phi by dt is p phi by 60 by n. That is my E average equals to p phi n by 60. So this is basically EMF induced in one conductor. Now for wave would the number of parallel path 2. Okay. So the number of conductor in series in one path Z by 2. Okay. Because total conductor is Z, number of parallel path 2. So number of conductor in series per parallel path is Z by A, and here A is 2 for wave winding, and for lap winding it is P. So it is becoming P phi Z. So we can simplify it. So this is my total generated voltage E equals to E average per conductor, and total conductor is in Z by A. So it is becoming P phi Zn by 60. Now A is 2 for wave winding and A is P for lap winding. So this is my final equation, P phi Zn by 60A. P phi Zn by 60A. So this is my EMF equation. In my later classes I will discuss the problem, and in my next class I will discuss the working principle and classifications of or types of DC machine. Okay. So this is all about today's lecture. These are the few reference book. Apart from this, you can also prefer Asfaq Hussain book or book by Mr. Purkait sir. Okay. Thank you.